Hello students, welcome to Eat Power Engineering class. Today we will review our last class session topics. We studied about universal gas constant. It is the product of gas constant and molecular mass of the gas. That is denoted by R of U is equal to capital M into capital R. And we also studied relationship between specific heats of at constant pressure and specific at constant volume. And in this class, we will study about characteristic gas constant and adiabatic index and some adiabatic index problems and multiple choice questions also. Characteristic gas constant. We know PV is equal to M into R into T. After simplification, we get R is equal to PV by MT. The unit of gas constant R may be obtained as below. So, what is the unit of R? So, R is equal to P into V divided by M into T. So, P is pressure, that is unit is Newton per meter square. V is volume, that is denoted by meter cube. The unit of volume is meter cube divided by mass in kg and temperature in kelvins. We can simplify here. Newton by meter square into meter cube. So, 2 this 2m and here 3m is there. 2 cancels and 1m remains. So, Newton and meter, that is Newton meter. In denominator there is no change and the unit of gas constant is equal to Newton meter per kg Kelvin. The Newton meter kg Kelvin, it can be written as joules per kg Kelvin also, because 1 Newton meter is equal to 1 joule. So, 1 Newton meter is equal to 1 joule. That is why instead of Newton meter per kg Kelvin, we write it as joules per kg Kelvin, where R is equal to characteristic gas constant or simply gas constant in kilojoules per kg Kelvin. P is equal to pressure of the gas in kg Kelvin, kilonewtons per meter square. V, volume of the gas in meter cube. T is equal to absolute temperature of the gas in Kelvin. M is equal to mass of the gas in kgs. The value of R is different for different gases, but is the same for particular gas. For air, the value of R is 0.287 kilojoules per kg Kelvin. So, R is different for different gases. For a particular gas, it is same, but for different gases, the value of R changes. Now we will go to adiabatic index. The two specific heats, that is specific at constant pressure and specific at constant volume of a gas, is an important constant in the field of thermodynamics, and it is represented by Greek letter gamma. So, Cp by Cv is equal to gamma. It is known as adiabatic index. So, Cp by Cv is equal to gamma. It is also known as adiabatic index. Since Cp is greater than Cv, the value of gamma is always greater than unity. Cp will be always greater than Cv. That is why the value of gamma is always more than 1. We know Cp minus Cv is equal to R. In previous classes we have proved it. So, Cp is equal to Cv plus R. Cp is equal to Cv plus R. That is the equation. Divide left hand side and right hand side, both sides by C of V. We get Cp divided by Cv. CV divided by CV and R divided by CV. CP by CV, it is nothing but gamma. So we can write it as gamma. And CV and CV cancels, one remains. And here R plus CV. So gamma is equal to 1 plus R by CV. So if we take 1 to left side, it becomes minus 1. That is gamma minus 1 is equal to R by C of V. If we take from denominator, if you send the C of V to left side, it becomes C of V, and from it goes to numerator, and gamma minus 1, if it take to RHS, it becomes denominator. Hence the result CV is equal to R divided by gamma minus 1. You have to remember it. Now we will solve some problems, simple problems. They are very easy. A certain gas has Cp is equal to 1.9 kilojoules per kg Kelvin and Cv is equal to 1.5 kg per kilojoules per kg Kelvin. Find the molecular mass of the gas and the gas constant. So you have to find the universal gas constant is given as 8.315 kilojoules per kg Kelvin. So in this problem, what we have to see, what are all the data he has given. He has given C of P, C of V and R of U, that is universal gas constant. What we have to find? We have to find R, that is gas constant, and M, that is molecular mass. And to find out that solution, we know R is equal to Cp minus Cv. That is very simple. Cp has given 1.96, substitute it, and Cv has given 1.5. After simplification, we get 4.46 kilojoules per kg. And we know this formula also. Molecular mass M is equal to, capital M is equal to R of U divided by R. Here we know what is R of U. It is already given in the problem. We know it. It is a constant 8.315 divided by, and we have got R as gas constant as 0.46. That is equal to, after simplification, it is 18.07. 18.07. Now we will go to the next problem. 1 kg of ideal gas is heated from 18.3 degrees Celsius to 93.4 degrees Celsius. Assuming R is equal to 264 kilojoules per kg Kelvin and gamma is equal to 1.18 for the gas, find specific heats, that is both specific heat at constant pressure and specific heat at constant volume, change in internal energy, that is D of U, change in enthalpy. You have to find these. So what all he has given? He has given mass is equal to 1 kg, initial temperature is equal to 18.3 degrees Celsius, but we have to convert it into Kelvin, that becomes 291.3 Kelvin. T of 2 is equal to, he has given 93.4 degrees Celsius plus 273, it becomes 366.4 Kelvin. R has given it as 0.264 kilojoules per kg Kelvin, and gamma also has given, it is 1.18, and he has asked for what to find. C of P is equal to what? C of V is equal to what? Du is equal to, you have to find out, and dH you have to find out, enthalpy you have to find out. Solution, we know C of V, that is specific heat at constant volume, is equal to R divided by gamma minus 1. So we know R is 0.264 and gamma is 1.18 minus 1. After simplification, we get 1.47. Cv is equal to 1.47 kilojoules per kg Kelvin. And the formula we know, specific heat at constant pressure is equal to gamma into C of V is equal to, we know gamma, it is 1.18 and we know CV also. Just now we have found out. After simplification, the answer is 1.73 kilojoules per kg Kelvin. Next, he has asked for internal energy, change in internal energy. The formula is D of U is equal to M into C of V into T2 minus T1. You know mass is 1 kg and C of V, we have found out specific heated constant volume, and T2 minus T1 after simplification it is, the answer is 110.4 kilojoules per kg Kelvin. Change in enthalpy. We know the formula dH is equal to M into C of V. Slightly some mistake is there. It should be C of P. C of P. T2 minus T1. Substitution is correct. 1 into 1.73 into 366.4 minus 291.3. The answer is 130 kilojoules per kg Kelvin. Here there is a small correction. Here in the formula there is a small correction. Instead of CV, please read it as C of P. That is specific heat at constant pressure. Now we will move on to multiple choice questions. The question is the value of gas constant R is. The value of gas constant R is 287 joules per kg Kelvin. That is the first choice. The second choice is 28.7 joules per kg Kelvin. The third choice is 2.87 joules per kg Kelvin. And the fourth choice is 0.287 joules per kg Kelvin. The correct answer is 287 joules per kg Kelvin. If it is in kilojoules, if this unit is in kilojoules, it will be 0.287 kilojoules per kg Kelvin. Since it is in joules, it is 287 joules per kilo, 287 joules per kg Kelvin. Thank you.